Well, thank you guys for being here. Some of you all may have heard some of this being spoken before, but I hope to talk to you guys a little bit about the public health model I've developed, and there's a lovely little preprint out now if you guys want to check it out. So yeah, thank you guys again for having me here. So the overall purpose of what I'm doing for my thesis is incorporating human behavior into different models of infectious disease, specifically regarding intervention strategies and how people feel about them. And so here we have, I'll be talking about the public health model specifically, but I'm currently working on a livestock model at the moment with some lovely farmer survey data, which is quite fun. And then I'll also be working on a crop model and just kind of like a review of like what's being done so far in this field. So for today, I'll focus on the public health model. And the motivating question behind this public health model is, how does subpopulation level information about intervention effectiveness impact epidemic severity? So during an outbreak, people might have some information about how well the vaccine is performing. And so that might change how likely they are to receive the vaccine or seek that out. And so here I explore pandemic influenza, SARS-CoV-2 and Ebola, purely because these pathogen systems have very different R0 values as well as mortality rates. And this is the overarching model that I've tried to simplify as much as I can here, but this is a typical SEIR type disease model. And the thing I would like to highlight here is the vaccine uptake. I'm calling this my behavioral function. And so the key part of this model that is different from others is, instead of having a fixed vaccine uptake rate, this changes based off of what behavioral group you are in, as well as what information you have on a day-to-day basis in the outbreak. So I'll go into describing this a little bit more. So we have the fixed, basically like a fixed vaccine uptake rate, which we would normally have. So some like reasonable estimate. I've been using 0.005 for this value, but then the important ones to note are vaccine opinion is this rho value, and then information sensitivity is this alpha. And so what the vaccine opinion does is it helps us break up our groups into subpopulations based off of their vaccine opinion. So we could have 0, which would mean they have a very low vaccine opinion. So they're very not likely to have, not as likely to have the vaccine, ranging from that to 2, which would be a high vaccine uptake relative to the other groups. And then information sensitivity impacts this theta value, which is our outbreak information. So this will end up being a ratio between 0 and 1. And that basically, I'll go into those calculations later, but the alpha of some information sensitivity gives us some idea of how sensitive people are to this information that they have. So then, this gives you an idea of, in general, what the uptake values might look like. So we can see that on the left, we have our vaccine resistant group, which has like very low levels of vaccine uptake. But then once you go through the vaccine hesitant and vaccine accepting groups, these end up being relatively like higher values that we can see. And then I'll walk us through how we calculate outbreak information. The 2 questions we have to answer here are, how many new cases are there since we last checked? And then, who do the new cases belong to? Are these from unvaccinated individuals, or are these from vaccinated individuals? And this sort of comparison will give us that outbreak information we're looking for. So on the left, this is day 7 of the outbreak, and the darker colored individuals are those that are infected. And then we have a nice little vaccine syringe here to indicate those who have been vaccinated at that point in time. So then from each of these points, we look at how many are of the cases, how many are unvaccinated and how many are vaccinated. And then from that, we say, okay, so since day 7, now on day 30, we now have these 4 new cases. So 3 of them come from unvaccinated individuals, and then 1 of them comes from vaccinated individuals. So then this is looking at sort of like the change since we last checked in terms of like, where do our cases belong? Like, who do those cases belong to? And so if we have a large number of the cases belonging to individuals who are unvaccinated at the time, that means that it's probably working. So then you would expect an increase in vaccine uptake. Are we all clear on that? Okay. Okay. Feel free to interrupt me with any questions you might have. And so again, this interpretation of our outbreak information is that if more of the new cases occur in unvaccinated individuals, then the vaccine's probably working and more people will get vaccinated. And I will go through these ternary plots because they're quite difficult to read. But given we have like 3 subpopulations, this is a good way to visualize that because we have 3 groups. And what are we looking for in this? So we have our vaccine resistant group on the left, vaccine accepting group on the right, and vaccine hesitant down below. I'm going to add a few things, kind of walk us through this. So as you go from the bottom left corner to the top vertex here, that means that the population that we're looking at is more resistant as you go to the top of the triangle here. And then as you go to this bottom right vertex, they're more accepting. And as you go to the left here, it's more vaccine resistant, or vaccine hesitant, sorry. So it's basically like what we're looking at is different configurations across this space. And we want to see how do our epidemic outputs at the end look based off of if we were to change the percent that belong to each of these groups. So in the middle, this would mean an equal split between the 3 subpopulations in a single simulation. And then as we go to the edges, we have a single behavioral group represented. And then there's space in between. So then what are we looking for when we see these crazy ternary plots? Question 1 is, are the cumulative epidemic metrics sensitive to behavioral configuration? So as we explore within this triangle, are values different that we get for maybe like number of cumulative cases in our outbreak? And question 2 is, are local cases or local deaths more beneficial as outbreak information? So as I was talking through the outbreak information, how we calculate that, we were talking about cases, but now we're introducing deaths as another measure, because we often see these 2 as being the ones that are reported from the public health sector, from the government. So we want to see, like, based off of the information that we get, deaths are lagged. Obviously, those happen later. So we have to kind of like wait for this information. So we want to see, based off of these different calculations, what we might see at the end. And then question 3 is, how do these differ by these pathogen systems that we introduced at the beginning? So we have pandemic influenza, we have SARS-CoV-2, and we have Ebola. And I'll just show the plots for Ebola virus, but then we'll, at the end, kind of summarize like how this differs with the different pathogens. So what we see here, this is information, the outbreak information was from local cases. So what we see here is that when information sensitivity is low, so this is 0.1, and then on the right is 0.2. On the left, when you have a lower information sensitivity, it essentially means that you're not reacting to what's actually going on throughout the outbreak as much. So of course, we would see more cases in that situation. And then as we look at, remember, like this top vertex, that's our most resistant configuration. And so it makes sense that we see that we have the most cases in that configuration versus the bottom right, which is the most accepting of the vaccine. And so what we want to see is sort of like, what are the variations that we see between these different situations? And in the right-hand plot, we see that as you get to the most accepting configuration, you actually get down to very, very low levels of cases, which is quite interesting. So this is on the order of like 10 to the second. So like that's essentially suppressing the outbreak at that point. So based solely on the configuration that you have behaviorally, then it's potentially possible to suppress the outbreaks. So now this bottom plot looks at this difference between local cases and local deaths. So if you were to look at local cases versus local deaths, what is the difference that we get? So this dark blue region indicates that we have a benefit of local deaths in that situation. And so essentially, just to kind of speed up through this a little bit, at the end of the day, it's local deaths are essentially leading to fewer cases at the end of the outbreak, if that's the information that we're getting. And with Ebola, we have a very high mortality rate, so we actually have a lot of information about deaths. So it's possible that local deaths might be, in the long term, more beneficial for us to look at for this particular pathogen system. Then when we look across these different pathogen systems, we have these two questions that we were asking at the beginning. So what we saw for Ebola was that, yes, the epidemic metrics are sensitive to behavioral configuration. Then the plots I didn't show you were for pandemic influenza and SARS-CoV-2. What we saw for those is that pandemic influenza was very similar to our findings from Ebola. But then for SARS-CoV-2, it almost like really didn't matter what your behavioral configuration was. It just didn't turn out well for anybody. So I think that was an interesting finding that we had. I think like the high R naught value probably explained a lot of that. And then for question 2, we're looking at is it local cases or local deaths that's more beneficial? So from Ebola, we found that local deaths was more beneficial. And then we found that to be similar with SARS-CoV-2 as well. And then pandemic influenza, we saw something a bit different. And I think because we have a very low mortality rate, we don't have a lot of information about what's going on with the deaths in these scenarios. I think it does make sense that we see that local cases kind of like gives us some information that changes our perception of like how the vaccine is performing. So then just to wrap up, what we found was that behavioral configuration alone can prevent disease spread in certain situations. And so this kind of relates to some of like the behavioral nudging behavior that we might see during outbreaks, and figuring out like, is it even worth it for us to change the underlying behavior of our system? Because in some systems, it might not be worth it if, depending on your behavioral configuration, even if you were the most accepting of the vaccine, it still might not end up well. And the second point I'd like to make is just that incorporating behavioral heterogeneity into infectious disease models is important in understanding how individuals adhere to the vaccine. And I'd like to thank my supervisors, and thank you all for being here, and I'll now take any questions. Thank you.